We have math for economists. We have a lecture with unknown number n. And we continue with linear programming. Okay. Once again, if you have any questions, just don't be shy. It's a good moment to ask them.
Is it possible to ask you to solve something like some
to solve?
Yes, like some problems with linear programming with some unknown parameters.
Yeah. That's okay. That's completely correct question. Obviously, I will not solve something that, for example, if you have a so I will not solve problems with exactly the same numbers as in home assignment.
Yeah, no problem. Yeah, something similar.
But something based on the same idea, no problem. Okay. So let's. Okay, the recording is fine. So yeah, we may go on. Okay, first I will do some new theory, but not so new, but some statement general about linear programming, and then we will solve the problem with parameter. So, okay, we will discuss maybe with some little proofs, yeah, some general statements, and then let's solve an example with parameter. Yeah, that's a very example. Parameter. Okay, so once again, we have two standard setup for linear programming problem. Standard maximization problem. Once again, everything I'm telling you is not a secret. Once upon a time, it was a fight between USSR and the USA who will invent linear programming first, because long time ago, almost a century ago, it was a known technique, and it allows very broad usage in forecasting economy of a country, and so that's why even if the if it was something like socialism and capitalism in USA, so even despite the difference in the system, it was a big state-powered research in that direction, but it was a long time ago, and now everything I'm telling you, you can find easily in Ferguson. I think it's a exposition with perfect style. So if you have missed something, if you need lecture notes with not my ugly writings, but with beautiful typeset formulas, so go. That's, I think, a book of choice is Ferguson. I don't remember, linear programming concise course or something like that. But if you Google like Ferguson linear programming, then you will find the PDF you need. Okay, so we have standard maximization problem is maximize C transpose times vector X subject to non-negativity constraint that all components of a vector X should be not less than 0, and meaningful system of linear inequalities like A is a matrix times X is not greater than B. So we have standard maximization problem, and we have a standard minimization problem, like minimize. We replace B by C and vice versa. So we have minimization of B transposed times Y, subject to Y is not less than 0, And A transpose times Y is, it was less, so now it's greater. Greater than what? And Ed, who can help me? What should I write here?
0.
Not 0. No.
C.
C. Yeah, you're right. We interchange B and C. B was here, and C was in the function, and now we have B in the function and C in the right-hand side of constraint. Yeah, we change B and C basically. Okay, and transposition for the matrix A. Okay, sometimes the problem is not standard. What can we do? So sometimes non-standard setup. What shall we do? What shall we do? So let's consider 3 examples. Example 1, when there is a mix of constraints, like, for example, you have maximization, y1 is greater than 0, y2 is greater than 0. You need to maximize, let's say, 5y1 plus 6y2. And you have 2 constraints, but the constraints are in wrong direction. Like 5y1 plus 6u2 minus, no, that won't be. Basically, I don't care about coefficients. They are greater than 7, and minus y1 plus 3y2 plus 5y3 is maybe minus less than 9. What shall I do? So my question is how to transform this problem to a standard form. What should I do?
First, minimize the function. Maybe we can find some correlations between 2 values like y1, y2, or y2, y3, or y1, y3.
Yes, that may be possible. Yeah, probably you're right, but there is a much shorter way to standardize. Probably you are right, but I think just look at what's wrong. Yeah, there we have maximization problem. Okay, we have maximization problem. Every x is greater than 0. We have y, but I don't care about the names of the variables. So that's okay. X, y, okay. Y, x, z, I don't care. What else? The inequality should be something linear is less than constant. The second one is correct. Something linear is less than constant. Yeah, Stepan is basically right. The problem is in this inequality sign. I need to reverse it to move to the standard form. Basically, what can I do to reverse the sign of inequality? Multiply by -1, and I'm happy. So I will just multiply by -1. So first recipe is multiply inequality with wrong sign by -1. So that's the first recipe. It's very easy. I just replace the first inequality by -5 y1 minus 2 y2 plus 3 y3 is less than -7. That's completely exactly the same system of inequalities, but just written in another form. So I have no problems when inequality has the wrong sign compared to the standard form. I just will multiply by -1 both sides of inequality, and I'm happy. Everyone is happy?
Yeah, super happy.
Okay, so what can be second problem? For example, something is missing. So what can be non-standard? When, let's imagine we have linear problem. So obviously we can have non-linear optimization problem. In that case, it can be approximated by linear problem. So that's what is done in real life applications. So you have a complex non-linear problem, but it can be approximated by a linear version near the equilibrium point. So what can also wrong? What can go wrong with linear setting? So okay, second example. Second example. Maybe non-negativity constraint is missing. So imagine 5y1 plus 6y2. We need to maximize. Y2 is greater than 0, but y1 is any number. It's non-standard problem, but we will transform it into standard. And some linear inequalities like 5y1 plus 2y2 minus plus y3 is less than 7, y1 minus y1 plus y2 minus y3 is less than 9. So it seems, how can I move to standard form? So it seems at first, it seems impossible how to move to standard form, standard maximization problem. At first, it seems impossible because I have no bounds for y1. Who has any ideas? What can I do? I should have exactly the same problem. So I cannot just say, let's add the constraint. That's a bad strategy because you will change maybe the solution, the best, the optimal solution, maybe it is in the region of negative y1. So you cannot just say, I will add the inequality that y1 is non-negative. So what to do in that?
Can we split onto two cases?
Yeah, we can split into two cases. Yeah, that's the first solution. Yeah, I completely agree that instead of this problem, you can split your problem into problem one, where y1 is greater than 0, and the problem two, where y1 is when minus y1 is greater than 0. And you may replace minus y1 by, let's say, z1. Yeah. And in that case, you have two problems to solve. Yeah, that's a possible strategy. And this problem number one, will be standard. So you can go to dual if you wish. So the problem number two will be standard. If you replace minus y1 by z1, that will be standard problem. And there is basically the same trick, but applied simultaneously. Solution two, you may just say that any real number can be represented by difference of non-negative numbers. y1 can be represented by z1 minus z2. So the second trick is to introduce new variable. So you will have more variables, but if you have a computer that is fine-tuned to solve very fast problems in standard form, then you can use this computer to solve non-standard form. So, and in this case, Z1, Z2 will be non-negative, because obviously any number, 5 or minus 10, can be represented by a difference of non-negative numbers. For example, 5 is 10 minus 5, and minus 5 is 5 minus 10. Yeah. So any real number can be represented by difference of non-negative numbers. So that's a cheap trick to transform problem with missing non-negativity constraint into a problem with non-negativity constraint present. Obviously, that increases the number of variables by one. Yeah, obviously, I will have my problem like maximize 5z1 minus z2 plus 6y2 z1 z2 greater than 0, y2 greater than 0. So, and the constraints. Yeah, so I will just plug in instead y1, I will plug in z1 minus z2. I will have 5 z1 minus z2 2 less than 7 minus z1 minus z2 2 less than 9 as far as I remember. Yeah, and that is standard problem. So basically, even if non-negativity constraint is missing, with a cheap trick, by paying the price of one more variable, you can introduce, you can transform this problem to standard one. And the last example of non-standard problem. No, the last example.
Can you please scroll up for a second?
Yeah.
Right here. Just a bit down so the solution 2 would be seen.
There is nothing below.
Yes. Great. Thank you.
So the trick, problem one that you can encounter easily on the exam. If the one of the inequalities has wrong sign, then that's not a problem. I will just reverse the sign of inequality by multiplying by -1. Second problem, if on the exam you see, be careful, that y1 is non-negative and y2 has no restrictions, then you can replace y2 by the difference of two variables, okay?
Yes.
Non-negative, and proceed like go to dual to reduce the number of variables to 2. So for the moment, we can solve two by hand. We will discuss a general method of solution that was invented almost a century ago, and it was a big breakthrough, like it was a big scientific discoveries. Let's say it is considered as one of the top 10 algorithms invented in previous century. Widely used now in portfolio optimization problems. Obviously, we do nothing by hand. Obviously, problems are too big. We have, let's say, 1,000 number of y1, y2, y3, and they represent proportions of some shares in the portfolio, and we need to locally optimize it given some constraints. But basically, it's widely used. But obviously not with 1 and 2 variables case. And by hand, we will, on the exam, you are required to solve by hand, let's say, problem with 2 variables and n constraints, and the problem with n variables and 2 constraints, because they are dual, and you obviously can go to the graphical, you can use a graphical approach. Okay, let's move on. I have discussed the last IDM, example 3. For example, you have some maximization problem. 611 plus, I don't care for the moment. X1 is non-negative, X2 is non-negative. I don't care about the coefficients, but the problem is that you have equality instead of inequality. You have 5x1 plus 2, or maybe I will add somewhere, because with 2 variables, that's too easy. 5, 4, x4 equal to 8, and I don't know, x1 plus x2 plus x3 minus x4 less than 6, x2 plus x3 minus 2x1 plus 2 plus 6x3 plus 2x4 is less than 10. What to do? It's a non-standard problem because I have equality. What should I do to have a standard problem, to use duality? I cannot use duality right now. What should I do?
Maybe use the first constraint where we have equality to replace some variables as a sum of others.
Yeah, there are two strategies. Yeah, the first strategy is just we can, so what is a possible solution, how to move to standard maximization problem. There is strategy 1, as you advised, you are completely right. You can, for example, take x4 and plug in it here, there, and there. You will obviously obtain constant in maximization function, but constant in the maximization function really does not influence the extremum point and only influences the optimal value. So you can subtract it and keep in mind that the optimal value is plus. So it's the first strategy. Express x4 in terms of x1, x2, x3, and plug in everywhere else. Everywhere else. That's the first strategy. Yeah, you're completely right. And I will get rid of a constant in a function optimized, and then I will go to the dual. Yeah, that's a good strategy, because when I will plug in x4 in, I will only 2 inequalities will remain. If I have a problem with 2 inequalities, I go to dual, and then I have a graphical solution. And there is a strategy 2. Strategy 2, it's a little bit, it may seem a little bit crazy, but if you have that left-hand side is equal to 8, you can just say, oh, it's equivalent that left-hand side is less than 8. Left-hand side is left-hand side is greater or equal than 8. And so you can replace, if you have a computer, and in that case, you can say something like, instead of 1 equality, you may have 2 inequalities. Left-hand side is less than 8, and the minus left-hand side is less than minus 8. And basically, I have 1 more inequality. But if I have a good numeric algorithm on a computer, Stepan, yeah, I will finish my, yeah, Stepan, you're right. I just forgot to look at the chat. Sorry. So I'm trying to look, but when I'm writing, sometimes I can miss. Yeah. So basically, I have transformed equality into 2 inequalities, standard form inequalities, and basically that's a possible strategy. Stepan is completely right. He spotted that I have missed x4 is non-negative. So either I should have in the original problem that condition, or I should use the trick we have used to replace x4 by difference of 2 non-negative variables. So either to have a standard form, either I should have this requirement in the setup of the problem, x4 is greater than 0. If I have no such information, then I can use the trick we have discussed 5 minutes ago, that we can, if this condition is missing in the problem, so be careful on the exam. So if it's missing, then you can either solve 2 cases or introduce represent x4 like difference x5 minus x6. Okay.
Excuse me, can you please explain the second strategy in example number 3, because I didn't really get it.
The second strategy.
Yes, yes.
Basically, this strategy is applicable when there are 2 scenarios: when we do problems by hand on the exam as first scenario, and the second scenario, if we have a computer, they are fine-tuned to solve standard form problems. So if I have a computer algorithm, I don't care where, in Python, R, Julia, I don't care where. So if I have a fine-tuned algorithm that solves linear programming problems very fast. So in that case, if I work with computer and I see that in my real problem, I have equality. Left-hand side, I don't know, 5x1 plus 2x2 plus 6x3 minus 7x4 is 8, exactly. So I can say, my computer says me, you should use matrix A. So the problem AX is less than equal to vector B. So in that case, I may replace 1 equality by 2 inequalities, and my computer algorithm will be happy. So I will just write 4 inequalities instead of 1 equality. So this I will keep number 2, number 3 I will keep, and number 1 I will have 1a and 1b. 1a will be 5x1 plus 2. So let me change the color. 1a will be 5x1 plus 2x2 plus 6x3 minus 7x4 is less or equal to 8. And minus 5x1 minus 2x2 minus 6x3 plus x4 is less than minus 8. And so I have 2 inequalities of the type 2 less than equal constant. And I have replaced 1. Maybe it's a bad idea to do it when you are on the exam by hand. But when you have a very fast algorithm that deals perfectly with standard problem, then that's a good strategy.
Yeah, thank you. Now it's clear. Thank you.
Okay, let's move on. So we have covered what we have covered. We have covered 3 possible deviations from standard form and how to deal with these 3 deviations, how to transform a non-standard maximization or minimization problem into a standard form. Sometimes it's very clear. Sometimes the problem on the exam is not in standard form. Okay, let's make some general theory a little bit. Now, the second moment. So first topic we have covered how to move from non-standard form to standard form. Then some theory. So we will have statement 1. Even we will prove it because it's very easy. Maybe definition. Yeah, definition. First definition. So we have a standard maximization problem that is maximize C transpose X subject to X greater than 0, A times X less than B. And we have, so let's recall standard minimization problem. we minimize B transpose to Y, subject to Y, all components of the vector Y are non-negative. A transpose to Y is greater than vector C. So we have two standard problems, and we call them dual. So first definition, we say that X is feasible for standard maximization problem if both constraints are satisfied. So if X is non-negative and AX is less than B. So feasible. Feasible, that means that all constraints are satisfied. Yeah? And by the same logic, we define what is feasible for standard minimization problem. Okay? So just a small term, feasible. That's very easy. Now we are ready to make first statement with proof. Statement 1. If X is feasible for standard maximization problem and Y is feasible for standard minimization problem, then C transpose X is not greater than B transpose Y. So what does it say? So if you just at randomly have chosen possible value of X, not optimal, but possible. So if you have chosen any value of X, but feasible value, yeah, any feasible value of X, and you have chosen at random any feasible value of Y, then maximum that you have attained, the value in maximization problem, is not greater the value in minimization problem. So basically, what you have C transpose X is less than or equal to B transpose Y. Okay, the statement is clear.
Yeah, it's clear enough.
Okay, let's go to the proof. Proof is very easy. So we will do it. Okay, C transpose X. What do we know about X? I know about X that A times X is, that's a part of my standard problem. AX is less than B. Yeah, that's a part of the standard problem. Okay, or I may say differently. Yeah, I may put it differently. I may, for example, calculate the transpose of I may what I can, if I look at that case, I see that I will just copy everything I need from the standard cases. Yeah. Or I may write it differently. That inequality is written in column form. So it is something like vector column is greater than another vector column. So I can take transpose of it. So if I take transpose of it, so it says that Y, so I will take transposition of a transpose of a matrix of both sides of inequality. So I would A transposed Y transposed is greater than C transposed. So basically that's the same statement, but written in row form. Wow, that's great. I remember the rules of transposition. It's YT A is greater than C transpose. And now that's half of the proof. We are almost finished. We say that is because vector C is less than YT times A and X is non-negative. Do not forget that X is non-negative. So using these two ideas, I can say that is less than YT transpose times A times X. And yoo-hoo! AX is less than B. And bingo, we have proved everything we would like for YT times B. And I have BT times V, but it's the same thing like YT times B, BT times Y is the same thing. Y is the same thing. Y, I can write Y BT times Y is YT times B. Why? It seems at first glance that the order of matrix multiplication has changed, and in general, when you change the order of matrix multiplication, you have done something wrong. But in that case, I'm playing on the safe side. Why I can do like that? Any idea?
It's 1-to-1.
1-to-1. What do I mean? What do you mean by 1-to-1?
It's a number.
Ah, yeah, I agree with you. Yeah. First, I've thought about 1-to-1 correspondence. Yeah, you are completely right. The size, the dimensions of this object, it's a scalar, it's a number. Yeah. Because what is BT times Y? It's B1, B2, B. I don't remember the number of is it N or M. Yn, and what is YT times B? It's Y1, Yn times B1, Bn, and basically both formulas are equal to sum of Yi times Bi and the same thing. Okay, we have proven a very interesting statement. Yeah. Yeah, the proof is finished. So what is the good conclusion? Conclusion that is already interesting. That is interesting conclusion. We have proven that C transposed X is less than B transposed Y. But remember that we are trying to maximize that value, and we are trying to minimize the right value. So we have a consequence that if for some X star and some Y star, I should point out for some feasible, yeah, for some feasible X star and for some feasible Y star, you have equality. BT X star is BT Y star. Then you cannot do better because you are limited for any feasible X You cannot go higher than the right-hand side as inequality. So if you have obtained inequality, oops, you have found two extremas at once, two extrema at once. Then X star is maximum and Y star is minimum in standard maximization and in the standard minimization problems correspondingly. Okay, so if we are lucky enough and we have found two values, X star and Y star, then they are optimal. Okay, let's go on.
Yeah, let's go.
Let's go on.
Boris Borisovich, can you scroll a little bit up?
Yet
A little more.
more.
Can you please explain what does like feasible X and Y mean? I don't get it still.
Feasible. That means for which inequalities are satisfied. So not outside our region we explore. So feasible means that it's for example, for standard maximization problems, is any vector X for which all components of X are non-negative and A times X is less or equals than B. So vector that all constraints are satisfied.
Okay, thank you.
So we just searching for the best X among feasible vectors. Okay.
Yeah, get it. Thank you.
So for example, if you consider, I don't know, that problem, yeah, the point 0, 0, 0, y1 is 0, y2 is 0, y3 is 0, is feasible because everything is satisfied. And the point 100, 100, 200 is not feasible because the first inequality is violated. Okay.
Yeah, okay.
So in any case, if something is, there is a good way to avoid my lectures. You just go to Ferguson. I don't remember what's the page, but I think it's in the beginning. So you just open the first. But I bet that it's something like not too far per page from 1 to 220. I think it's in the beginning. Okay, so, and the next statement will be without proof. One more theorem. So this will be, yeah, without proof. And it says that basically first order for linear programming, first order conditions and second order conditions. So we need not to check. So the meaning of this theorem, we do not need to check second order conditions in linear programming problems. So basically in linear programming, in standard form, in both problems, first order conditions are sufficient. Or to be more precise, let's say, so basically the intuition is, the intuitive meaning is very easy. I don't remember, it's called equilibrium theorem in Ferguson. because it has interpretation in terms of game theory, and so it is so the name, it has a name, equilibrium theorem. Basically, it says first order condition are enough to be sure that we have attained maximum or minimum. So if x star is feasible for standard maximization problem, and y star is feasible for standard minimization problem, mean for standard minimization problem. Then x, y, and x star and y star are optimal. And that's important that we have here if and only if, and only if. So we have, so the theorem guarantees us that these conditions are sufficient. So we should have if and only if. How should I write? If I have too many ifs. If x1 if x1 is feasible, then x1 is feasible if and only if. And then I should write first order conditions for our problems. Basically, they are roughly that Lagrange multiplier. So basically, they should be something like lambda times TL d lambda is equal to 0. Basically, first order conditions, they are of this type. And then it's easy to write them if you understand the logic behind. That behind we have a lambda times dl d lambda equal to 0. So we are happy to write them. If and only if for every non-active inequality, for every non-active inequality of S max, for every non-active inequality, let's call it I, of S max, of standard maximization problem, the corresponding y I is equal to 0, and for every non-active inequality of I of S mean problem, the corresponding x is 0. So basically, these are the first order and second order sufficient conditions. That's all. So basically, what we need to check, we need to check that when some inequality is non-active, then the corresponding Lagrange multiplier is 0. So we will, for the moment, we will omit the proof, basically after internal exam, we will do some proofs. But for the moment, we will omit the proof. If you are interested, you can check the proof of equilibrium theorem in Ferguson. But basically, that says the only thing we need to check is the rule that either Lagrange multiplier is 0, either the inequality is active. You cannot have simultaneously non-active inequality and positive Lagrange multiplier. Okay, the meaning of the theorem is clear. Any questions?
I want to know, is there any special case or is it general result for all the functions?
For all the linear, so that theorem works for all standard form linear programming problems. So it's a general result for all linear linear programming problems in standard form. If you have a linear programming problem in non-standard form, you can transform it to standard form. We have discussed how. If you have a non-linear optimization problem, then the duality is a little bit harder to get, but we will go through duality in non-linear case. It's a little bit more difficult, but we will deal with it in some weeks. So for linear, it's the general theorem for all. So because it's a theorem, yeah. If you don't believe me, you can check the proof in Ferguson, or wait, I think we will prove something later. So it's a honest theorem.
But if these two values multiply then equal to 0, which one is exactly equal to 0? Or there are three cases, like first one equal to 0, second one equal to 0.
Yeah, basically, yes. And that says if this, so what is this statement? This statement, if non-active inequality, so that means dl d lambda is not equal to 0, then the corresponding y, that is Lagrange multiplier, we should remember that y, so maybe just a small recap, that y is a Lagrange multiplier or inequality on inequality on x1 xn, and xi is a Lagrange multiplier for inequality on y1 ym. Yeah, so there is a duality. Y is a Lagrange multiplier, but it's Lagrange multiplier for inequalities about x. X is a Lagrange multiplier, but for inequality about y1, y2, and so on. Okay, any questions?
No questions.
Okay, let's solve some problems with parameters. Let's go and solve a problem with parameters. So basically, we have finished with theory. We have, I think, we have 20 minutes. So let's be fast. Let's example with parameters. With parameter. Okay. So I will have a minimization problem. So I will add arbitrary numbers here for the moment. Let's say 2 x 2y1 plus 3y2 plus y3. I need to minimize that, given that I will start from standard form, because we know how to move to standard form if we start from non-standard form. I will have 3 variables, but 2 inequalities. I will have something like lambda y1 plus y2 plus y3 is greater than 5, and 2y1 plus y2 plus 3y3 is greater than greater than 7. Okay, that's my problem. Okay. And the goal is to find the optimal value for each possible lambda. Yeah, the problem is clear. Any questions about the statement?
No question.
Okay. So first idea. If you can go to graphical solution, so choose graphical solution if possible. Obviously, I have a theorem that guarantees me, just write first order condition using Lagrangian function and be happy. You don't need, so the theorem is very powerful. It says you don't need to check in DCQ, you don't need to check second order condition in linear case. You can just write first order condition and you win. But I have a parameter, and it will be ugly mess if I just blindly write these inequalities, equalities in first order condition. So the theorem, I'm on the safe side. The theorem says me ignore in DCQ in that case, not in other cases. Ignore second order conditions. Just write first order conditions and be happy. But I will go to dual. So my first step, I go to dual problem. So I have a maximization problem. I have 5 and 7. So I will have 5x1 plus 7x2. I have coefficients 2, 3, and 1 in the optimized function. So I will have x1 is greater than 0, x2 greater than 0, and I have 2, 3, 1. I write 2, 3, 1 is the right-hand side. I have a standard problem, so it's transformed in a standard way. I just take this matrix. I have lambda 2 in the first column, so it will be lambda x1 plus 2x2. For the second column, I have 1, 1 coefficients. And for the last column, I have 1x1 plus 3x2. I have now a problem that I can solve on a plot. That's much easier to work with a 2 dimensions plot than with 3-dimensional optimization problem. Everyone is with me or everyone is lost? Everything is
I'm
fine?
here always.
Yeah, it's clear.
Okay, let's move on. So I will solve my problem graphically. It's much easier. And theorem guarantees me just check first order condition. So I will draw my constraints. X1 is non-negative, X2 is non-negative, so I work in the first quadrant. So I have line 1, line 2, line 3. Line 2 and line 3 are fixed, and line 1 is rotating. So I will first draw line 2 and line 3, and then I will draw rotating line 1. Okay, line 2, that is 3, that is 3, and then go line 2. So line 2 is on the plot. I go with line 3. Line 3, x1 is 1, x1 is 1. X, oh, it's 1/3. Oh, I have chosen numbers at random, so I will redraw my plot. I will redraw because my plot is too small to understand something. So the feasible region is that small triangle. I need also to draw the first line. The first line. If x1 is 0, x2 is 1. And line 1 is a rotating line, because if I express x2, so lambda y x1 plus 2x2 equals to 2, x2 is 1 minus lambda times x1. So my line number 1 can go through this point 1, and line 1 is rotating line. Okay, any questions?
Isn't x2 equal to 1 minus lambda multiplied by x1 and divided by 2?
Yeah, it's my fault. Yeah, you are completely right. It doesn't influence the plot because it's rotating, but you are completely right. Yeah. Okay, I will redraw my plot because don't be lazy to redraw. If something is too small on your plot, just spend 1 minute and redraw the plot. So I see, oh yeah, and I will move on to the next page. Just I will copy these two useful inequalities. One, the number 3, we will use number 3 and number 1. Number 2 is obviously non-active. Lambda x1 plus 2x2 and 2. If the number will be more complicated, like the center is not 1, is root of 2, the value of we got is simultaneous or exact the number. I don't understand what is simultaneous. The value we got is simultaneous or exact the number. I don't understand your question. If you should work with square root of 2. If you are not told to calculate approximately, then you work with square root of 2. Okay, I will redraw my plot. This is 1/3. That is x1, that is x2, that is 1, that is line number 3. I have this is 1, and basically there are only basically 2 cases how my red line can go. There is first case, case 1. Red line does not intersect my feasible triangle. So case 1, I have a feasible triangle, and red line goes like that. That is case 1. And basically I have case 2. Case 2, when my red line intersects feasible triangle and cuts a part of my feasible triangle. So in that case, the feasible region will be not, in case 2, the feasible region is not a full black triangle, but a smaller region. So that is a feasible case, feasible set. And in that case, the full triangle is a feasible set. Like the answer will be 1 dot number 2 number will be round a to b. So if you are not required to round in the text of the problem, so you work with exact numbers. Like if something is square root of 2, you just write square root of 2. So if you are not required to make approximate calculations, so you do exact calculations.
Thank you.
Okay, let's move on. What's the function we are trying to minimize or maximize? I forgot. Man, that's ugly. Then I need to switch pages. Okay, I need to maximize 5x1 plus 7x2. I need to maximize 5x1 plus 7x2. Let's draw the level curve. The level curve x2 is c over 7 minus 5 over 7x1. So my level curve, let me draw it in blue. That's a level curve of my function that I'm trying to optimize. Level set, level curve, it's straight line. And my straight line goes like 5 over 7. It's a negative slope, but for this line, the slope is minus 1 over 3, because I know this is 1 over 3, this is 1. So the slope is 1 or minus 1 over 3. And my slope of the optimized function is minus 5 over 7. So if I plot on the same, plot on the same graph my feasible triangle, let's forget for the moment about let's forget for the moment about the red rotating line. I have something like that. That is my level curves. Level curves. And the optimal point is point, let's call it, we know it's 0, 1. 0, 1 is x star, yeah. Okay. Any questions for the moment?
No, that's clear.
Okay, so we have already solved case 1 is solved. Case 1 is solved. When the first rotating line
I guess it's the other way around. No, it's 1, 0. No.
Yeah, right. Yeah. I completely, yeah, you're perfectly right. That is x1. I have missed the first is 1, is second is 0. Yeah. Okay, case 1 is solved. If my red line is far above my feasible triangle, then I'm happy. The optimal point is found. Okay, let's solve. And the optimal value in that case is 5 times 1 plus 7 times 0 is 5. Okay, case 1 is solved. Let's move on to case 2. Yeah, we are ready to move to case 2. Any questions?
No questions.
Okay. Case 2. And now I see the problem that I will have 2 subcases because case 2, I have case 2.1 and case 2.2. This is my black triangle. 1 over 3, 1, 1 over 3, 1, x1, x2, x1, x2. If my line is very has a very big negative slope. Imagine that red line has very big negative slope. It's like that. And so the feasible region is very small. In that case, or maybe I shouldn't draw it like that. No, let's make a little bit. Oh, like that. Because otherwise everything is at the same point. Okay, in that case, my blue line, level curve of my optimized function. It has x2 is c over 7 minus 5 over 7x1. It has a slope minus 5 over 7. And it is it's like between the small slope of triangle and big slope of the red rotating line. So my slope of my optimized function is between the slope of the red rotating line and the slope of triangle. In that case, the optimal point is x. Oh, maybe it's better to call it a, the optimal point. And case 2-1. So this is the idea when the slope of the rotating line. So what is the condition for case 2-1? Slope of rotating line is negative and is less than minus 5 over 7. That is case 2-1. And I have basically one more case when or maybe no, maybe I have no. Let's consider what is the extreme case. So if I go like that, so for the moment, the slope is, so for the moment, the slope is -1. If I go from the point 1, 0, yeah. And there is a small case when the slope of my red rotating line is not so small as it is. So I will have, let me draw maybe a case and it will explain itself. 1, x2. Oh, it's red. It should be black. 103. Okay. If my rotating line will move, will be, no, I have no case 2. Oh, I'm happy. Yeah, the time is up and I'm happy that I'm wrong and there will be no case 2. Yeah, no case 2. Yeah, I'm very happy. Because if I will have a line like that, the slope will be exactly less than -1. And if the slope is less than -1, so I conclude that in that case, the slope is less than -5 over 7. So the hypothetical case 2, when the slope of rotating line is less than -1 over 3, but bigger then minus 1 over 7. So this case 2 does not exist. Does not exist. And I'm very happy because I don't need to consider 3 cases, and I need to consider only 2 cases in that problem. Oh, we have 41 minutes, but I will finish very fast, and maybe if you have some time, you can. So I have basically 2 solutions. What is the slope of rotating line? What is the slope of rotating line? The slope of rotating line, the rotating line has a formula like x2 is 1 minus lambda over 2 x1. So the slope of rotating line is minus lambda over 2. And basically, I have 2 cases. When minus lambda over 2 is less than, is greater than, is less than minus 1. So I will have, in this case, I have case 2, 1. If minus lambda over 2 is greater than minus 1, so I have case 1. So basically, if lambda is less than 2, I have case 1. Case 1. If lambda is greater than 2, I have case 2, 1. In that case, we know that optimal value is 5. We have already solved it. And we need to finish the solution of case 2, 1. Case 2, 1, we need to find intersection of line 3 and the intersection of line 3 with rotating line. That is the optimal point A. So we need to find intersection of line 1 that is rotating and line 3. If I need to find the intersection of 2 lines, I will just solve the system of equations. x1 plus 3x3 is 1, and lambda x1 plus 2x2 is 2. Woohoo! That's a linear system of equations, and I can solve it. Once again, I will copy my system. X1 plus 3x2 is 1. Lambda x1 plus 2x2 is 2. What can I do to solve it? Let's pre-multiply first equation by lambda. I will have lambda x1 plus 3 lambda x2 is lambda. I subtract it from the first one, and I have 2 minus 3 lambda times x2 is 2 minus lambda. So x2 is 2 minus lambda over 2 minus 3 lambda. And to find the x1, x1 is 1 minus 3x2, and it's equal to 1 minus 6 minus 3 lambda over 2 minus 3 lambda, and it is 2 minus 3 lambda minus 6 plus 3 lambda. 2 minus 3 lambda is minus 4 over 2 minus 3 lambdas. Okay, and we have almost finished case 2, 1. The optimal value is 5x1 plus 7x2. It is 5 times minus 4 over 2 minus 3 lambdas. But there the lambda is restricted with 2 over 3. Why lambda is restricted by 2 over 3? I don't remember. It was compared with 2, I think.
For x1, because 2 minus 3 lambda cannot be equal to 0.
If I remember, we have case 2(1) works when lambda is greater than 2. So I think we will have no problem. If lambda is greater than 2, we have no divisions. We have no division by 0.
Yeah, thank you. Sorry.
Plus 7 times 2 minus lambda over 2 minus 3 lambda. And basically, we have the final answer. The final answer. The optimal value is equal to 5 if lambda is less than 2. And if I add these two terms, I will have 14 minus 20 is minus 6. Minus 6 minus 7 lambda over 2 minus 3 lambda. Yeah? Minus 6 minus 7 lambda if lambda is greater than 2. And I need to add equality somewhere. So it doesn't matter where you will add equality because the function is continuous. That's an important point, that the change in our picture is continuous. So I may, for example, add equality to the first case, to the second case, doesn't matter. Basically, that's all. Okay, any questions?
Thank you. It's okay for me.
Boris Borisovich, can you go up, please, to the case 2-2?
Yeah. In the imaginary case, so imagine that our triangle will be not the right point. Imagine the case when the right point was at the point, let's say 5. Yeah, imagine a case when you have so imagine a case when you have 1 over 3 here, 5. Imagine like that to change. And the level curve has slope. So here's the slope is minus 1 over 15, very small. So the slope of the target function of optimized function is minus 5 over 7. And we are rotating a line. We are rotating a line that starts in a point 1. And in that case, you may have a situation in that imaginary case that is not realized in our problem. We may have a situation when we have the rotating line goes like that. And in that case, the slope is so the slope of the rotating line is minus lambda over 2. And it may be the case 2-2. At first, I thought that we have a case 2-2. And in that imaginary case, the optimal value is at the point B. Yeah. But in our problem, we have no case 2-2. So it is imaginary. Imaginary case 2-2. Why we have no case 2-2? Because even if because the smallest possible slope for red rotating line is when it goes through the rightmost point of the triangle. And in that case, the slope of rotating line is already -1. And so it's already less than the point, the slope of target function -5/7. So we have no imaginary case 2 in our case. That is imaginary case for very flat, very flat triangle.
Yeah, I understood. Thank you.
Okay, so at first, because I have invented a problem by your request, so it was not prepared beforehand. So I have asked in the beginning of the class, what are your problems? So what is the most difficult? And there was a request to invent a problem with parameter. So, okay, I have invented from my head a problem with parameter. And so at first I thought that there will be another case when the red, when the red angle is between blue and black angle, but that's not possible in my problem. Okay.
Yeah, I see now. Thank you very much.
Okay, any more questions?
I want to know if in exam we face such kind of problems, we just need to write down the function, do not need too much for explanation part, is that right?
But the level of explanation I have provided is sufficient on the exam, so it's okay. I understand that. So the level of explanation, it's always a difficult question whether I should explain too much or so. Right, as you are trying to explain to, imagine that you are explaining a problem to your friend. For me, the reasonable level of explanation when you try to explain the problem to a friend, and your friend understands you, then that's a perfect level of explanation.
Okay. And today, because this part is connected with linear algebra, so is that possible we have a task which connected with linear algebra and the Lagrange function?
Sorry, I don't understand the question.
I mean, is that possible for Lagrange function and linear algebra working in the same time? Like it's a complement.
You may use Lagrangian function to solve this problem, yes. But my advice, always choose a graphical approach because it's simpler.
Okay, great.
It's possible. So if it's not possible, you have 11 problems, or so if you have a problem or hard problem with n, x1, x2, xn, no, I don't know how to move something to. So if I have 3 variables, okay, it's tough. But if you have an option to go with graphical approach, go with graphical approach.
Okay, thank you.
Okay, that's all for today. Have a nice evening. See you next time.
Have a nice evening. See you tomorrow, Boris.
Thank you.
Bye-bye.
Goodbye.
Yeah,
Okay.
thank you. Goodbye.